Hello, my name's Matt Wright. Today I'm going to talk to you about Dirac delta functions, which is an important mathematical tool that we're going to use in E&M a whole bunch. So for starters, let's look at a nice simple step function. Right? It's got x and y. So our step function is going to be 0 everywhere, right? Except at some point, it's going to come to some height a. The step function is going to be centered around a point little a, and it's going to have a width of 2 epsilon. So the entire width is 2 epsilon. Okay. Now, one of the cool things about this step function is it's easy to calculate the area, right? So the area of this is just its height times its width. So it's going to be the area, it's going to be the A, the height here, times how wide it is, which is 2 epsilon. Now, if we're really going to be talking about something called a Dirac delta function, this area is equal to 1. Cool. So, for deltas, for a delta function, the area is equal to 1. That's a property of the delta function. We can solve for the height. Okay. So one property of the delta function is that the area is 1. Another property of the delta function is that it's a spike. In fact, whenever we're in physics and we need to model something with a spike, it's really good to think Dirac delta function. It's a spike. So that means that the width of the delta function is really, 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 really small. But I know the area has to be 1 over 2 over epsilon. So if I make epsilon go to 0, what must happen to the height? The height must go to infinity. So what you get is you get something that looks like this. A delta function, hold on for a second, minus a, of course, right? So we move it, doesn't have to be right at the origin. It's going to be 0 whenever x doesn't equal a, and it's going to be infinity when x equals a. So it's like we've taken this little step function and we've squeezed it. We've squeezed it so small where the area still has to be 1, but by squeezing it so small, infinitesimally small, the amplitude of it has to shoot up to infinity. Right? So to keep area 1, when you make it infinitesimally small, the height has to go to infinity. So you get this really interesting property where the delta is of x minus a is equal to 0 everywhere else, and it's equal to infinity right at x equal a. Okay. So how can we use this to our advantage? Imagine we have the following integral. Some function of x times the delta function, x minus a, times dx. Well, if we choose this model here, the model of the step function, right, and we take a look at it below, maybe here, your delta function is 0 everywhere except for one point where you get a small spike at x equal a. But your function f of x is going to be curvy, doing whatever that f of x does. Over this infinitesimally small region, f of x doesn't change. Or it doesn't change much, right? We can treat it as a de facto constant. Right? So then this gets pulled out. We get to ignore everything else because there the delta function's 0. So you get f of a times the integral from minus infinity to infinity of delta x minus a dx. And well, this is just telling me what is the area under the delta function. Well, that's just simply 1. So this integral becomes just f of a. All right, let's do an example. Okay, let's start with this example. We have an f of x here. It's x squared, right? We have our delta function, which has an argument of x minus 2. And we're integrating it from minus 10 to 10. What would be the result of this integral? Well, my f of x is equal to x squared, and my a is equal to 2. So the answer is going to be f of a, or 2 squared, which is 4. Okay, let's do another example. Let's look at this. Okay, well, remember how the model is. The model for the delta function looks like delta x minus a. So what is a going to be here? Well, here, a is going to be minus 2. Right? If I plug in minus 2 for a minus times a minus gives me the plus 2. There my delta, there my a is minus 2. So when I evaluate this, it becomes minus 2 cubed, or minus 8. Interesting. Okay. Okay, what am I going to get here? Well, I'm doing my integral from minus 10 to 10. What value is a? Well, here, the value of a is 11. So remember what our plot looked like. We're starting our integral at minus 10, and we're going to 10. Where would the spike be? Well, the spike happens at the value of a, which here is 11. So the spike happens here, and it's 0 everywhere else. So it's 0 on the range from minus 10 to 10. It never sees the spike because the spike happens at a equals 11. So this integral, since it's happening over this range where there's no spike, is simply 0. Okay, one more. What's that integral? I'll let you think about it.